Good evening. My name is Aditya Sharma, and this is Aircraft Propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the National Program on Technology Enhanced Learning. And this is a 12-week course. So at present, we are into week 6 of this course, and pertaining to that week, we have this live tutorial session. Okay. This session is being recorded and later will be uploaded on YouTube. So today's theme is intake and nozzle. We shall see discussion around these two topics, and then we will do some questions based on these topics. Okay. So let's just wait for a few minutes before starting. So in few minutes we'll start the session. Okay, so we can start with today's session. Instructor for the course is Professor Vinayak Kulkarni from again Department of Mechanical Engineering, IIT Guwahati. Okay, and I'm a research scholar here, also a Prime Minister's Research Fellow, pursuing my PhD, the Professor Niranjan Saud. So let's see the contents of this particular session. Sorry. Yes. So three lectures are there. Lecture number 17, lecture number 18, lecture number 19. So as I was saying that the theme is intake and nozzles. So first lecture is nozzle flow. So in nozzle flow, you'll see isentropic relations, area velocity relation. What is mass flow rate in the nozzle when it's choked? We should see this. Then we have next is intake. So aircraft engine intake, and then efficiency of the intake has been discussed. Ram efficiency, okay, intake efficiency. So these things have been discussed. Then is your propelling nozzle and its efficiency. So the nozzle that we will fit in the engine after the turbine. So that has been discussed in lecture number 19. But then I don't have questions on this lecture, but we will still discuss this lecture. So we can begin with the topics of lecture number 17. Isentropic relations, area velocity relation, flow through nozzle, choke mass flow rate, then area Mach number relation. So we are well versed with the isentropic relations, but still I'll just write these down. In the study of aircraft propulsion, the knowledge of these isentropic relations proves to be very handy for us. Okay, because we have to, this is basically showing you an ideal case. All right, so we can use this to compare with the reality, the real, like in the previous lecture, we saw previous week's lectures, we saw real cycle. So first we saw Brayton cycle, and then we saw the real version of Brayton cycle. So there also we first see in isentropic relations, you can relate the stagnation property with static property. The numerator is stagnation and the denominator is static. So 1 plus gamma minus 1 by 2 m squared. Okay. So this is for temperature. And then for your pressure, stagnation pressure to static pressure, this can be done this way. Okay. Then talking about density, we can give density this way. Gamma is the ratio of specific needs. So this is your isentropic relations. Already. Just give me a second. Okay. Then after isentropic relations, your one-dimensional inviscid compressible flow relations have been discussed. Okay. So for your momentum equation, in case of compressible flows, if we see one-dimensional inviscid compressible flow, here momentum equation, so this becomes P1 plus conservation of momentum, okay, E2 plus rho 2 E2 square. This is that, and then from here, few other things have been discussed. After that, you have moved on to area velocity relation. So what is area velocity relation? So Sir has worked this out, whole expression. How do you get this? Okay, I'll just write down the final expression, which is changing your area by area is equal to m square minus 1 du by u. Okay. So what is this equation telling us? So on one hand, we have change in area. On the other hand, we have change in velocity. Also, then we have Mach. This basically says that, let's say we have some duct, okay, in which your air is or some fluid is flowing. So if you move from A dash to B dash, what do you see is that your cross-sectional area is increasing in this direction. Okay. In that case, your BA, change in area, will be positive. Correct? So if your change in area is positive, implies EA by A. This will be positive, which implies your left hand side is positive. Okay. Now, in such case, whatever the situation may be, the right hand side will adjust itself in such a way that eventually it will come out to be a positive value, right? So if your Mach is greater than 1, let's say your flow is supersonic. So let M be greater than 1. In that case, your M square 1 is what? Positive. So M square minus 1 is positive. Right? So your velocity, your denominator is already positive. Then change. So whether the change will be positive or negative. So change again will have to be positive. Multiplying positive with positive will give positive. So which implies your du will be positive. On the other hand, that Mach is less than 1. In that case, what will happen? Your M square minus 1 will be negative. So for right hand side to be positive, your change in velocity will have to be negative. Correct? So in this case, your velocity will increase. In this case, your velocity will decrease. So this is your supersonic case. This is your supersonic case. This is your subsonic case. Okay. So this essentially means is if your duct is divergent, right? It is diverging. Okay? This is converging, this is diverging. So if your duct is diverging, in that case, what will happen? In that case, if the flow is supersonic, then it will further become supersonic. If the flow is subsonic, then its velocity will further reduce. So if the Mach is, let's say, 0.7, in that case, as the flow is moving forward from A dash to B dash, the velocity, the Mach will come down to be lower than this. Okay. So this is your area velocity relation. And next is your flow through nozzle. Very important topic as far as the uh, topic nozzle is concerned. So if we understand this flow, so we understand the uh, nozzle, working of nozzle. flow through nozzle. Okay. So I'll just first draw a CD nozzle. Okay. This is your inlet. This is your outlet. Okay. This is your pressure along the length of nozzle. This is that distance. So this is your reservoir pressure or stagnation pressure. Here, P naught. Then add the nozzle. This is P star. Okay. This is overexpanded case. Then something like this is your underexpanded case. One more diagram has been drawn that is related to mass flow rate, that is in the nozzle. We exit by P naught. This is mass flow rate. Okay. Maybe this. So what is happening here is we have at the inlet we have some pressure, all right, that we call as stagnation pressure, and at the exit we have some back pressure. This pressure difference between inlet and outlet, between this stagnation pressure and this back pressure, is driving the flow across the nozzle. Okay. And as we keep on decreasing the pressure, this back pressure, the flow through nozzle changes. So how it changes, that let's see. So let's say at some point we have this back pressure. So in this case, if you see this section up to throat, your flow is, your pressure is decreasing. It means your flow is accelerating, right? And beyond the throat is pressure increasing, which means your flow is decelerating. Then if you see second, here also, if we further decrease the back pressure, this is, and then comes a point, this third situation, where what happens is the throat gets choked. Okay. So at throat, the pressure will not fall beyond this point, even if you keep on decreasing the back pressure. So this basically is the idea. And this condition is your choked condition. Because once your nozzle is choked, so that will define the maximum mass flow rate that can pass through a nozzle. Okay. Now beyond this, if you again decrease the back pressure, right, your flow will, beyond the throat, again your pressure will decrease. That means your flow is accelerating, right? Before this, it was decelerating, but now it is further, it is accelerating. And what happens because of this is your exit pressure. So your exit pressure somewhere here becomes less than your back pressure, right? And then this ends up in a condition that we call as over expanded condition, right? The flow has over expanded. In case your exit pressure is, the exit pressure is greater than P back pressure, in that case you have under expanded. So there is still probability of it expanding. Okay. Here P exit is less than P back. This has flow has over expanded. And one is this ideal case where your exit pressure equals the back pressure. This is how flow in nozzle behaves. with back pressure. Hope this is understood. So this also figure is showing the same information that beyond a certain point, if you keep decreasing the back pressure rate, the mass flow rate will remain same. Okay. So this is giving ratio of P exit by P naught, and this is your mass flow rate. Then is choke mass flow rate. Since I have discussed, expression for choke mass flow rate has been given. Which is P naught by this gamma by R, 1 plus gamma minus 1 by 2 minus gamma plus 1 by 2 gamma minus 1. Then we have A star, the area at the throat. So this is, I believe, the expression for a choke mass flow rate. Okay, P naught is stagnation, T naught is stagnation temperature, gamma we know, R is universal constant. So all these expressions, all these parameters, properties we know what they mean. Then is area Mach number relation. Based on some at some place in your nozzle along the its length, based on the information of area, we can predict the Mach number. So this is A by A star square equals to 1 by M square, 2 by gamma plus 1, 1 plus gamma minus 1 by 2 M square, gamma plus 1 by gamma minus 1. So this is your area. So let's say if you see the figure, let's say you have some area at this section, you have some area. This is some area A. Yes. Let's say this is some area A. So this is your area A star. Okay. Now if you see this equation, this is your map that is to be predicted at area A. Right? Gamma is ratio of specificity, so this way we can work this out. So this is it about topics from lecture number 17. Then let's see questions based on nozzle flow. Please have a look at this question and then we will discuss this. So we have question number 1, which says that for flow through a choked nozzle, the mass flow rate of air. Then we have 4 options. First option says that it depends only on downstream conditions of the nozzle. Depends on both upstream and downstream conditions of the nozzle. Is independent of upstream conditions of nozzle. Is independent of downstream conditions of nozzle. So to answer this, we can visit the expression for choked mass flow rate. So to find the mass flow rate in choked condition, the properties, parameters that we require are, one is so related to flow, if you see parameters or properties of flow. So one is your stagnation pressure, and then second is your stagnation temperature. So these two we require. Then whether, now question asks in terms of upstream and downstream. So P naught and T naught. P naught and T naught. So whether they are downstream properties or upstream properties. So they are upstream properties. Okay. So your mass flow rate depends on upstream properties, and it doesn't depend on downstream properties. So essentially, the upstream knowledge of upstream properties will suffice to answer this, to know the mass flow. So fourth option is independent of downstream conditions of the harvest. Comes out to be the correct option for this question. I hope this is clear and there is no doubt. If so, you can just type in the comment box and let me know. I'll be happy to answer and discuss. Then we have next question. So please have a look at the question first, and then we will discuss this question. Okay, so second question we have. Let's read this question. This says that for incompressible flow through the nozzle, the velocity dash and the pressure dash while flowing through it. So the question says first is incompressible, then says nozzle, then says what happens to velocity, then says what happens to pressure while flowing through it. Okay. Then incompressible, if it is, then Mach is less than 0.3 for air. Mach is less than 0.3. which means this is subsonic. For subsonic flow, what happens? Now you go to area velocity relation. So let's see if this is for your. So we discussed for a diffuser. So for diffuser, we discussed that if your flow is subsonic, in that case, the velocity will decrease. Yes. So what will happen if your duct is in nozzle shape? Duct is acting as a nozzle. So if the duct is acting as a diffuser, in that case, velocity will decrease for subsonic cases. But if the duct is acting as a nozzle, in that case, for subsonic flows, the velocity will du will be positive. The velocity will increase. Velocity will increase. And if velocity is increasing, pressure decreases. Okay. So this is the formula. M square minus 1 du by this is what M square minus 1 will be negative here. For your nozzle, if you talk about nozzle, dA will be negative. Okay. In that case, to keep left hand side negative, your du will be okay. So A is the correct answer to this question. Then next is question number 3. Which of the following is correct for fluid flow through a duct of converging passage? Please read this question. Also, the options that have been given. Let's read the options. First option is only works as nozzle if inlet flow is supersonic. So nozzle means your flow will accelerate. Okay. Diffuser means your flow is decelerate. Okay. So second option is always behaves as a diffuser for supersonic inlet. Only works as diffuser if the inlet flow is subsonic. Always behaves as nozzle. So for converging passage, This is converging passage. dA is negative. Ky is m square minus 1 du by u. For subsonic case, what will happen? This will be negative. This is again negative. So du will be positive, which means accelerating, which means it is acting as a nozzle. For supersonic case, m is greater than 1. M square, this will be positive. Okay. Now dA is negative for converging. So if this is positive, so this will have to be negative. U is negative. Flow is decelerating, which means it will act as a diffuser. Now let's see our questions. Subsonic, supersonic. Only works as nozzle if the inlet flow is supersonic. For supersonic, it will act as nozzle. For supersonic, it will act as nozzle. No, first option is not correct. Always behaves as diffuser for, for supersonic inlet. Behaves as diffuser for supersonic inlet. B seems to be right. Only works as diffuser if the flow is subsonic. This doesn't seem to be right. Always behaves as nozzle. This is also not right. So B seems to be correct option. B is also the answer to this question. This is clear, I hope. If not, please make a comment in the comment box in the YouTube video when it will be uploaded. I can answer there. So let's see the next question. In that case, please read the question first. Also the options, and then we will discuss this question. So the question says that, question number 4, the flow through nozzle is considered to be underexpanded when the nozzle outlet pressure nozzle outlet pressure is okay. So the nozzle outlet pressure I have discussed as exit pressure, and ambient pressure I have discussed as back pressure. With your ambient conditions, you are taking as your back pressure. You are giving the stagnation pressure through some reservoir in that case. So when is your flow under expanded? The flow is under expanded when you see this diagram. When your exit, see this, when your exit pressure is greater than your back pressure. Okay. So P outlet has to be greater than P ambient. In that case, there is again possibility of flow getting expanded. So P outlet greater than P ambient. Ambient. So seeing the option C seems to be the right option. And if you see the answer, so C is the right. Okay. So now we will take a short 5 minutes break. After that, we will continue with the session. Thank you. Let's continue the session. The next question is this question number 5. Please have a look at the question. It says that convergent divergent duct acts as a nozzle for flow with dash. If it is a nozzle, then flow will have to accelerate. And this talks about CD nozzle. So we have discussed CD nozzle. For convergent case, this has to be subsonic. Okay. Sorry. And for divergent case, from divergent, it will have to be supersonic. Okay. It will have to further accelerate because divergent case, again, it will have to be supersonic. It will have to continue expanding. And then at the exit, you will have a supersonic flow. So we're seeing the options. B is the correct option. Okay. You see this diagram. Pressure is decreasing in the first half, means this is acting as a nozzle, flow is accelerating. Then again in the second half, for the ideal case, if you see, again pressure is decreasing, it means the flow is again expanding. So we expect the nozzle to behave ideally. I hope this is clear. B is the correct answer to this question. The next question. The fluid pressure along the length of duct dash for supersonic inlet through the diverging duct. Diverging duct has been given. We have discussed diverging duct. Also, what is given is Mach greater than 1. Then what's your discussion, previous discussion? Area Mach number relation for supersonic diverging. This is This is diverging case, supersonic diverging case. What happens is your du is positive. Your du is positive, which means velocity will increase, and in that case, pressure will decrease. Fluid pressure along the length of the decreases. Now this is clear. There is the right answer to this question. Next question, for particular reservoir conditions, the flow in at the minimum cross section area of the choked CD nozzle should be, sorry, there is some, okay. The answer popped up before the options. Anyways, so we can discuss this again. So for CD nozzle, flow at the minimum cross section of the choked CD nozzle. Flow at the minimum cross section of the should be what? It should be sonic. Okay. At the duct, at the throat, sorry. The throat, at the throat, your MAC is 1 when the throat is choked. When MAC is 1, the throat is choked. Okay. So this was question number 7. Then we are done with discussion on lecture number 17. So now we'll have discussion on lecture number 18 and lecture number 19. Okay. So Vishal has just joined. So we have discussed lecture number 17 and questions related to that. Now we are moving on to lecture number 18. So we'll discuss lecture number 18 and lecture number 19. I have questions, few questions for lecture number 18 only. And for lecture number 19, I don't have questions because it's a very small lecture, 20 minutes lecture. So let's first briefly discuss the topics of lecture number 18 and 19, then we shall see. Or I believe we'll first discuss topics and questions of lecture number 18 and then we should see lecture number 19. So this lecture number 18 is on aircraft intake and the efficiency of this intake. The topics are aircraft intake and then mass per rate and intake and mass per rate. Then comes compression that happens at the intake of engine. Then there are types of modes of operation in your supersonic intake. Then intake efficiency, RAM efficiency, this has been discussed. If you see topic lecture number 18, if you see aircraft engine intake. First of all, different types of intakes have discussed, like your S bend intake, straight through intake, like 2D rectangular intake, conical intake, annular intake, hidden or buried intake. So all these have been briefly discussed. Then comes is your intake and mass flow rate. So at any point, if Vishal, if you have to ask something, you can just ask. So intake and mass flow rate. So first is in this two categories have been discussed. First is your high speed and low mass flow rate. Okay, so I'll just draw the diagram of it. PS diagram. This difference basically is the loss in the total pressure while we are taking while the intake of air is taking place. So this is delta P naught. Intake pressure loss this basically is. Not wrong. Okay. Diagram is something like this. Okay. Here like this. This is two. This is one. And from somewhere here it is coming like this. Right. something like this. This is your stream tube, and this is your A. It's just a tiny. Okay. So this is your high speed and low mass flow rate case. So the stream tube area will be this small, this one. So from A to 1, first flow moves, right? Though here it has been shown this isentropic, but in reality it will again not be isentropic. Later in one diagram, this has been shown. I believe in intake efficiency. And then from 1 to 2, this has been shown as real change. Okay, from 1 to 2, this has been shown. And in this process, there is loss in total pressure. Ideally, it should have been P not 1, but then because of loss of pressure, we get this change reduced to P not 2. Also, T not 1 is equal to T not 2. So in diagram, this will has not been cleared like, too accurately, but these 2 points will fall in same on the vertical axis. These will fall on same point. Okay, so the flow is pretty better. Then is your next diagram. That is for your low speed and high mass flow. Let's draw the diagram here again for discussion. 4 lines and this. This, this, this. When these 2 points should fall vertically on the same level. This is A, this is 1. This is pressure at inlet. This is P2, this is P02, this is P01. Again here if you see, as the air enters the intake and reaches the compressor, so at that point, from the point where it started to enter your engine, right? And then it enters the compressor. So up to that point, it encounters loss in total pressure. So this is this, right? So this is it. Here it looks like this. Something like this. And the stream tube here is wider in comparison to your previous case. Okay. This frame. A1, 2. This is for your second case. So these two cases, and because your this area is more, in that case your mass flow rate is high. Intake mass flow rate is high. Then few other things have been discussed under this topic. One is external and internal compression. External compression is what is happening here. This is coming under external compression. And this is coming under internal compression. All right. Supersonic intake, there are three modes. There is supersonic intake. There are three modes. These modes are based on where you have the normal shock. In the intake, at what place you have the normal shock, based on that, this has been defined. So first is your subcritical mode, then is your critical mode, then is your supercritical mode. Okay. So based on back pressure, if you see, this would have high, this will have low, and this will have low back pressure. Then mass flow rate, if you see, this will have low mass flow rate, this will have high mass flow rate, and this will have high mass flow rate. I have not drawn the scenario. Let me draw the scenario of how the shock, where the shock is. The shock will be slightly away from the, so if this is the direction of flow, okay, this is the direction of flow. Shock will be slightly away from your this. This is called, yes, this is called throat end. This is called highlight and throat. Terminology are there, okay. Then for your critical case, this will be attached to your intake. Okay. So as to your input. For your supercritical case, your shock will be inside this, and then there will be outside this also there will be one external shock. Okay. This is shock, shock, internal shock. This is external shock. Okay. Then intake efficiency has been discussed. Okay. Intake efficiency just for this section, for the stream tube section. Here, stream tube section. Diagram is like this. I should draw this more slant. Then this will come. From A to 1 not, not 1 and not A. So ideally 1 dash, 1 dash. But in real case, this is moving in this to here, and then this is the stagnation condition for this intake efficiency. And if you have to define the isentropic efficiency, Ni, how do you define it? T naught 1 minus T A. So based on the temperatures. T naught 1 minus T A. So TA is this position. These two temperatures. First is this temperature, and second is this temperature. T naught A minus A is in the denominator, T naught 1 dash minus TA is in the numerator. So this can be used to define the intake efficiency. Then there is also RAM efficiency, NR, RAM efficiency. Which is based on pressure data. So this is this. This is your RAM efficiency. Then there are questions on this. I've done some mistake in preparing the slide. That is fine, but we can discuss this. Okay. Just check. Take time to. Anyways, so question number 8, select the correct statement from the following statements concerning the intake function of a subsonic aircraft engine. So this is for intake function of a subsonic aircraft engine. So it increases the kinetic head of air at the entry of engine. This is the first option. Second option is it supplies air to the compressor at low pressure. It reduces heat loss in the combustion chamber. It increases the pressure of air at the entry of compressor. So the purpose of your subsonic aircraft engines intake basically is to increase the pressure of air at the entry of your compressor. All right. This was your question number 8. Then next is your question number 9. So this says that RAM and intake efficiencies are same and interchangeable. So whether this is correct or not. So this is also a correct statement. Right. So your this and this can be used interchangeably for your intake of aircraft engine. So this is a true statement. This is correct. Right. Then we have last question. Last question to this session. So the question is this: for a supersonic air intake, which of the following statements is correct? So two options have been given, two statements have been given, and based on that, we have to give a correct statement. So first is for a supersonic air intake, which of the following statement is correct? First is back pressure of critical mode of operation is higher than subcritical mode. So whether this is correct or not. Second is subcritical mode of operation sees both internal and external shock. First, if you see back pressure of critical mode of operation is higher than subcritical mode. This is not a correct statement. If you go back pressure of the subcritical mode is highest and supercritical mode is lowest. Supercritical mode is highest and critical mode is lower, but the statement says opposite. So first is not a correct option. This is a false statement. First statement is false. Then talking about second statement, subcritical mode of operation sees both internal and external shock. Sub, so it's not the subcritical mode that sees both internal and external shocks. It's the supercritical mode. So see the supercritical mode. So supercritical mode sees both external and internal shocks, not the subcritical mode. So again, this statement is wrong. So both the statements are wrong. So based on the given options, so option number D comes out to be a wrong option. So sequence of animation, there was flaw in that in few questions. Okay. So this was at about lecture number 18 on aircraft engine intake. Then propelling nozzle and nozzle efficiency. So these two topics are left. So we'll discuss these two topics and then we will just conclude this session. Lecture number 19. First is your propelling nozzle. What is a propelling nozzle? I'll just draw this diagram again. So first we have a compressor. If you see the Brayton cycle, we have a compressor. Then we have a combustion chamber. Then we have a turbine. Then we have a nozzle. This way it has been drawn in your lecture. This is your compressor. This is combustion chamber. This is turbine, and then you have nozzle to again accelerate your this working fluid coming out of your turbine, which eventually is the jet of your engine. Okay. Then two cases have been discussed. One is where your nozzle is choked and other is where nozzle is not choked. So it has been discussed that you need some pressure is there. So below that pressure, if your working fluid expands, in that case, the flow is choked, otherwise that is not. So diagrams have been drawn for that. And then after that, nozzle efficiency has been given. I'll just draw this diagram. So this basically is what is happening in your nozzle. So from your turbine exit, and so we assume that from the at the entry of nozzle, so the conditions are stagnant and kinetic energy we neglect. And in that case, when your nozzle is used, okay, so ideally it should move from not 4 to 5 dash 5 prime, but then it is moving from, in real scenario, it is moving from not 4 to position 5. Okay. And then, so there is one, this pressure PC. Okay. If your pressure at after this passing through the nozzle is less than this pressure, in that case, this is choke. Okay. Choke means maximum mass flow rate, otherwise it's unchoked. If that pressure is greater than the ambient pressure. So nozzle efficiency you can write this way: n subscript j, eta subscript j, P naught 4 minus T5, P naught 4 minus T5. So this is your basically nozzle efficiency. So this is it about today's session. I'll conclude today's session in that case, and if you have some query question, you can ask, always ask. So there were 3 lectures. First lecture was on nozzle flow, and next lecture, lecture number 18, was on aircraft engine intake. Third, last was on the, so lecture number 17 was on fundamentals of your nozzle. So how the flow behaves in how the flow behaves in a CD nozzle. Okay, all this was there. And in lecture number 19, the application part was there, that how this is used, this nozzle is used in your aircraft engines, and then as a propelling nozzle, and then how the efficiency of that can be calculated, worked out. And then we saw a few questions, 7 questions from lecture number 17, and 3 questions from lecture number 80. Right? And this way we did our today's session. So thank you for joining this session. The next session again will be on coming Tuesday with same timing 6 to 8 p.m. Till then, bye.